Hello everyone, I'm Luke from Cocos. Hope you had a great day. We've been working on some great videos, and today is no exception. So let's get started and learn something about Cocos Creator. This video is about shaders and how to use them. Some developers might be new to shaders. Shaders is a difficult topic, and so it's usually something not taught. Shaders are used in APIs, GPUs, CPUs, and other things. So it takes some time to get to know the subject. But as a game developer, when you start building complex games, you need to know. So we've decided to create an entry-level video series on them to help you. Even if you don't use Cocos Creator, this series should be very helpful to you. I will introduce some basic knowledge on how they work using Cocos Creator, from simple lightweight versions to more complex. We'll also discuss how to use WebGL with shaders, and take a look at how rendering pipelines work. You've probably heard rendering pipelines before. It's a process all developers need to know when rendering a game. Some additional things we'll discuss are what the GPU and the CPU need for rendering, and why they have different types and needs for shaders. Figuratively speaking, the CPU is a bit like a water park pipe. It's very fast but only handles one task at a time. But due to the infrastructure of a CPU, large amount of data and logic passes through quickly. So dealing with some larger tasks is efficient, but processing images isn't that great, because the logic of processing images isn't that complex. But you need to share thousands of pixels of that image at once. And so you need to have multiple processes happening at the same time. So a CPU can't do that. But a GPU can do this. The GPU consists of a large number of small processing units, so it doesn't process as well as the CPU, but the GPU can handle processes in parallel. The CPU and the GPU are both required for the entire rendering process. The CPU is the truck sending the boxes of algorithms, while the GPU picks up the boxes and processes all the boxes at the same time. So, the final assembled image is completed at one time. Since we want to draw an image, you will want to interact with an underlying API. This is where WebGL rendering happens. What is WebGL? WebGL is a 3D drawing standard running in JavaScript. The OpenGL interface isn't very rigorous, because OpenGL itself is a set of specifications. Before this set of standards, major graphic manufacturers like AMD, NVIDIA, Intel, and others had their own set of APIs to call on graphics. This made development difficult with different APIs to work on. Therefore, a set of specifications was built called OpenGL. OpenGL specifications unifies the API interface, so developers don't worry about which API is built off on, just worry about one. WebGL is a layer of packages on the basis of OpenGL. The essence of the underlying layer is still OpenGL. The use of WebGL to draw points, lines, triangles are according to code, so you can build a lot of complex scenes for the web. WebGL is running on the GPU, so you need to use software that can run on the GPU. Such a graphic software needs to be provided in pairs. They will need both a vertex shader and a fragment shader. And we use the GLSL language. Combining these helps in the drawing process. So anything in WebGL that is in 3D space will have a final output to the gamer of a 2D window. So most of the work done in the rendering engine is converting 3D coordinates to 2D pixels. The WebGL rendering pipeline can handle this work. This main process is divided into two steps. The first step is to convert 3D coordinates into 2D coordinates. The second step is converting these 2D coordinates into pixels. These two processes are divided into several phases. Each stage input will use the output of the previous stage. Let's take a look at this in a picture. This figure contains multiple stages of graphical rendering pipeline. Each stage will handle its own part of the responsibility in the process of converting the vertex data to the final pixel. Next, let's take a look at the functions of each stage of the pipeline. The vertex data is used to provide processing for the backed vertex shader and other stages. It is the main source of data for rendering pipelines. The data input of the rendering pipelines includes the vertex coordinates, texture coordinates, vertex normals, vertex colors, and other vertex properties. WebGL passes the corresponding information according to the rendering commands. Common primitives included will eventually draw these vertices or lines or triangles. The vertex data and matrices come from the CPU. The vertex data passes the vertex shader. This is where you introduce data into the cache area. Then it is passed from the CPU to the GPU. Then it specifies the resolution method to that vertex shader to get data from the cache area. The matrix, on the other hand, can be passed by the means of the uniform, similar to a global variable. The vertices in WebGL are unable to get the data between passes, so they can get the information from the matrix conversion information. Next is the vertex shader. The main function of the vertex shader is coordinate transformation. It takes a single vertex as input and transforms that vertex from local to clipped coordinates. In fact, convert 3D coordinates in the game into another 3D coordinate. So, let's look at this picture. Usually we work with the local coordinates in the developer tools. Of course, there are also tools that operate directly on the world's coordinates, but this will take a layer of conversion. If it is a local coordinate, you need to convert the local coordinate to the world coordinate through the model transform matrix. So how is an object rendered and determined by the camera? The world coordinates need to be converted to the observation space through the observation matrix. Finally, we convert the crop space through the projection matrix. Then the next stage is assembly phase. The set of all the vertices output by the vertex shader becomes the input. Depending on the specified command, such as whether to draw as a point, a line, or a surface, the assembles all the points into that shape. For example, we offer two vertices. Do the two vertices have to connect into a line, or do multiple line segments connect together? This is all determined by the instructions in the assembly phase of the drawing element. Once the elements are assembled, it will also go to the screen mapping to determine the final points that need to be drawn on the screen. Then we can start the rasterization operation. The rasterization phase will traverse the pixels and determine whether they fall into the assembled figure. If the pixel is inside the graph, the next coloring operation is performed on the pixel. Interpolation of the non-vertex positions is also performed. We give each of the pixels other information as well. Next, we enter the fragment shader. The fragment shader mainly colors the pixels. Light calculations and shadows are also processed in the stage for better effects. After all the corresponding color values are processed, we can go to the last stage, the alpha test and mixing phase. This phase detects the depth of the fragment, uses that to determine the pixel is in front or behind objects, and then determines what should be discarded, and then checks the alpha value for transparency if it needs to mix objects. So even in the fragment shader, the color of the pixel output is always calculated. The last pixel color is also completed when they're rendering multiple triangles. So you can see the graphics rendering pipeline is very complex and contains a lot of configurations. So let's take a step-by-step look at understanding how shaders work. In the previous part, I said that coloring process is written in the GLSL language. So let's take a look at the foundation of the GLSL language. The GLSL is a tailor-made for graphics because it has features for vertex and matrix operations. A shader typically contains an input and an output variable, and a uniform and main function. The entry point of the shader is from the main function, and all the input variables in the main function and output them into an output variables. Let's take a common vertex shader and fragment shader for example. If we look at the vertex shader, the opening attribute is declared as an input attribute. The names of the properties show that the values are vertex position, vertex texture coordinate, and vertex color. Don't worry if you don't follow all of this, because we'll be talking about attributes later. And also, what are vertex coordinates and colors? Just know that they're inputs and output attributes that are given. These pass the vertex color and vertex texture coordinates to the fragment shader. Note that the vertex data is not directly passed to the fragment shader, but the data can be passed down between phases. So you need to give the data to the vertex shader and then pass to the fragment shader. Finally, the process vertices are passed to the GL built-in variable GL position for the GL to process. The vertex location declaration here can be vec3 or vec4. A built-in variable GL position is ultimately needed for vec4. If the input is vec3, it is possible to turn it into a vec4 when it passes. Now, let's look at the fragment shader. After the vertex properties output, the fragment shader needs to declare variables with the same name to receive them, and then use that uniform to declare 2D texture. The final 2D texture and the vertex color are passed to the GL fragment's built-in variable GL frag color. passing GL processing color information. If you just draw a solid color graph, you can also pass any textures. Next, let's look at above shaders and the shaders we'll be using in the future, as well as the usage of some variables, modifiers, and scenarios involved. For more information on how to use it, please refer to the link below in this video. You can check it out and learn more about GLSL. So I recommend everyone to check it out. Of course, you can also go directly to the GLSL official website to learn more. Now, let's look at the variables and the variable types. I think everyone understands this, so let's be brief. Just focus on the usage of floating point matrices and the usage of textures. Let's look at one of the following ways to use it. The first is scale. Scalar usage. Using scales are directly declared. At the same time, the conversion scalar and the floating point values can be performed. Let's take a look at the vector. A vector can be obtained by directly declaring the vector plus the value of a vector that directly fills each component. You can also assign each component directly. You can also make a copy of the vector value, and the calculation of the use of the vector in the matrix is characteristic by the unit. You can also fill the vector. For example, vector plus scalar combination or vector component recombination. But remember not to exceed the length of the original vector. Next, let's look at the matrix. The matrix is actually similar to the vector, so we can skip this. Next, look at the interaction of the vector, scalar, and matrix. In fact, you only need to understand that the vectors and matrices can be manipulated component by component. The following content is actually quite simple. Let's take a look at the qualifier. Qualifiers are divided into storage qualifiers, parameter qualifiers, precision qualifiers. Let's take a look at the storage qualifier. Storage qualifiers are divided into 3 items. Uniform global variable, and these are global variables assigned values before the shader. They are globally running. Attribute as seen as before is an attribute, and data transferred by the application to the vertex shader, including what a vertex position, vertex color, and other things are declared through the attribute. There's also the varying variable. It is used for data transfers between vertex shaders and fragment shaders. The statement must be consistent between the two shaders. As we saw earlier, output of the vertex color and vertex texture coordinates to the fragment shader. That statement is made by varying. The second is the parameter qualifier. Parameter qualifiers include these 3 sizes: in, out, and in-out. A bit similar to writing in C++. It's actually a parameter passing process. If you use the in modifier, it only means that the parameter is copied at one level. All modifications to this parameter in the function are modified to this copy, not affecting the original value. Out represents the parameter for output. It has not been initialized when entering the function, but when the function is over, it can be used as a return value to the return operation. Then, in-out stands for referencing passing. After the value is assigned at the beginning, it is no longer a copy but a reference relationship. Modify this value within the function, and the value is modified value after the end of the function. You can specify the accuracy of the shaping or floating point variables. Accuracy limits are divided into high precision, medium precision, and low precision. Their representative ranges are shown on this chart. The precision qualifier can be declared at the beginning to determine the precision of all int and float types. Of course, you can also set a single shape and a floating point setting. Then the above is a list of all the ones you will use in these video tutorials, like variable, modifier, and common usage. Then we finally look at the 2 concepts that after you finish this video. These 2 are the state machine and the context, respectively. Most elements on WebGL can be described in terms of state. For example, whenever a shading is enabled, whether textures is enabled, whether blending is enabled, or whether depth test is enabled, usually WebGL will execute the default state, unless we call the related interface to change it. For example, do we want to enable a light? Then we decide to enable a light through GL enable something something, or use GL disable something 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 to disable the light. This belongs to a state adjustment. Switching the status appears frequently in our video tutorial, so it's good for everyone to understand this. The last one is the context. WebGL needs to rely on the canvas carrier to get corresponding drawn contexts. So the context is about drawing. Call the corresponding drawing API through the drawing context, including the various state switches mentioned above. Every object is drawn. You need to set a series of status values. Then run a coloring method by calling GLDrawArrays or GLDrawElements, and make the shader run on the GPU. WebGL's rendering context is created as shown in the figure above. The above part is some basic knowledge about shaders. In the next episode, we'll be building a triangle. So we'll see you in the next video.